Yeah, so it's really nice to have Abhirup Datta as our colloquium speaker today. Perhaps a few of you know him already. Abhirup is a radio astronomer currently based at IIT Indore. Abhirup's PhD was from NRAO in the US in 2010, after which he was a NASA fellow and then a research associate at UC Boulder until 2015. He moved to Indore in 2015, and he has been contributing to the development of the astronomy, astrophysics, and space engineering department there since then. So Abhirup's research interests are mostly in using radio astronomy for solving cosmological problems, and he has made important contributions, particularly centered around the square kilometer array, the next big thing in radio astronomy. And Abhirup is also currently the co-chair of the Epoch of Reionization Science Working Group within the SKA. It's a really nice treat to have Abhirup present this over Zoom. We thank you for agreeing to talk over Zoom, Abhirup. Hopefully you'll visit us physically at some point soon. But otherwise you can start the talk now.
Yeah, thanks, Rishi, and thanks, Girish, for this invite. I'm happy to be zooming in into TIFR, and we'll like to visit a moment the situations becomes better and conducive. So yeah, so today I was basically invited to give an update on what is happening in this cosmic reionization, cosmic dawn to Epoch of Reionization thing, and mainly in context of SKA, the Square Kilometre Array. And it's very important because it's one of the very important key science goals for Square Kilometre Array, and India is a global partner in this particular telescope. At least there is still some final hurdles to cross, and we keep our fingers crossed that those will be decided in favor. But yeah, so far, the Indian effort is being led by NCRA TIFR in Pune, which is, of course, associated with the TIFR, Bombay. And we have formed an SK India consortium. A lot of institutes all across India are members. And so everybody has a member on the EC and so on. This particular science goal, Cosmic Dawn and Epoch of Reionization, is a part of a combined science working group from Indian perspective, which is also attached with the cosmology part. And a lot of members here, Girish, myself, and others. I think Rishi may be also a part of that particular science working group from the Indian perspective. And there is a lot of activity going on, which I will just briefly touch a few of them in this particular talk. Okay, yeah, so before we start, I think to just set up the kind of the platform, what are we talking about? So if you can look into my cursor, so this is basically on the right hand side where you see the Big Bang, where is the beginning of everything, and the universe expanded, it became cool, it stayed neutral through this entire dark age, till the first stars, galaxies, black holes forms, and then they start reionizing the universe. Now, we have studied the cosmology, all the intergalactic medium stuff from the present day till this era, but the neutral fraction becomes so high at this particular era that there is nothing can be done by using the standard probe Lyman alpha forest. So here, nothing was done for a long time, till the probe. It was not a new probe, it was already predicted long time back in 80s. I think that you can use the spin flip transition of neutral hydrogen, where the ground state, the lab frequency is 1.4 gigahertz. So if you redshift it to this epochs like redshift 8 or 9, that will come around lower than 200 megahertz. The main problem is this signal is very faint, and you cannot detect it unless you have a super sensitive instrument like we are having now. Okay, it will be. It is also this cases of detecting the primordial pancakes, that was the term used that time, is also in the very design of GMRT when it was built. So there was supposed to be a 50 megahertz feed also, and the 150 megahertz feed. They complemented each other. The compact design of GMRT also is basically to detect this kind of large-scale structures. But so be it. So I think it was not done for a long time because the instrumentation at this lower wavelength, lower frequencies or larger wavelength was not exactly matching the sensitivity requirement for this kind of science to be done. But with the advent of LOFAR, the MWA, and now we are gearing up for the SKA, I think now it's the right time to look into this, and there already has been several upper limits which are coming up in the precursor pathfinder instruments. So there are a lot of things to be learned. What are the nature of the first stars, first galaxies, black holes, how the universe reionized, whether it was just a step function, like it was instantaneous phase transition, or it was extended epoch. All those are the questions which people are trying to explore by looking into this particular epoch. This is how it looks like. I think Girish probably have better visuals for this. Just to make the case evident, this is the area which we are probing, the Epoch of Reionization cosmic dawn. And if you see, this is how the models so far looks like in the simulations. And you can see the top panel is showing you the frequency, the redshifted frequency, and the bottom panel is the redshift. It's not very clear, but the take-home point is this is what it should look like if you make a tomographic image. Okay, if you are basically taking a all-sky average signal, this is what it looks like in the differential brightness domain for a global signal, which we'll also come to. And then this is where you are probing individual scales. So you're looking in spatial fluctuations of the neutral hydrogen from this particular epoch. So this is what the predictions are. And we'll see and go more. So just first look at the global experiments. Means you're looking at, you have a single radiometer, single telescope, you're looking at the sky, you have a very large beam, so you're averaging over the large part of the sky, so you are not sensitive to the spatial fluctuations in this H1, but you are looking for a global signal. So here what you are seeing is this is the differential brightness temperature against the CMB at the background, and you can see this is the lower panel is showing you the redshift, starting from 25 on the right hand side, going down to 6 on the left hand side, and on the top you are seeing the redshifted frequency kind of going up from 60-ish megahertz to 200 megahertz. Okay, so this is what it should look like. This is a prediction, nobody has treated it yet. Confirmatively, there is a tentative detection which is not exactly convincing so far. But anyway, we'll come to that. So the major instruments were here. Yeah.
Amulya, just have a question. Just try to understand this figure. So what does this tell you? That tells me that what happens around 14 to 16 redshift?
Yeah. So this is basically, you have the, this is the cosmic dawn absorption. Basically, whenever you have this coupling, Lyman alpha coupling, where the Lyman alpha is produced by the first stars, this you have the absorption because you have a coupling between the kinetic temperature and the spin temperature, and which causes this absorption trough against the CMB.
So I should see a drop between 80 to 90 megahertz. Is that
right? Well, there are several models. So depending on how you play with the parameters, this can be quite deep, quite narrow, quite broad, and like this. This is one particular model.
Okay.
Don't
so this basically
biased by
around 80 to 90 megahertz signal is absorbed. You will see less number of photons of this frequency.
Yeah, so 80 to 90, typically you should be able to see, but there are predictions that it may also happen in the little bit higher redshifts. Also, those models are also there.
Okay.
So I'm not showing those gallery of models over here, but
no, I just wanted to understand what this plot means. The exact numbers
okay.
are not.
Okay, so basically against the CMB, you should see an absorption.
Okay.
If you are looking at this, so if you are having a single radiometer, and if you are looking at the sky at this frequency, this is what actually edges have detected. At least that's a claim. Okay. Yeah.
Thanks.
Hi, and then finally, if you are going
can you tell what is this kinetic and spin temperature that you mentioned? What are those?
Spin temperature is basically the excitation temperature of 21 centimeter line, the high profile transition line. And TK is the gas temperature.
So the transition temperature and the gas temperature.
Yeah.
Okay. Okay, you can proceed. Yeah.
Okay. So essentially, these are the experiments, 3 experiments which are shown over here. One is the edges, which initially were just designed to look into the frequencies above 100 megahertz. So in the Epoch of Reionization era, but they also started building and instruments which are going to the lower band. So there is a edges experiment which was conducted from 50 to 100 and 100 to 200 megahertz. And so they have some interesting results, or had interesting results a few years back, and that was been debated, further analyzed, reanalyzed, and there is a bit of a consensus right now, which may be the cause of the signal, and it may not be the actual detection. Apart from that, there are various other experiments going on. SARAS, which is nearest to us, which is RRI-led experiment, initially started by Ravi Subramanian, and now I think it's continued by people like Saurav Singh, Mayuri, and others. So this is one of their design of antennas. They also had various change in the instrument design, and now I think the current status is that they have putting it up in somewhere in the middle of a lake to avoid some reflections, which is the main cause of worry for the edges signal. And there are Prism, which is in the Marian Island, basically in a pristine part of the globe where there is no reflections, no radio frequency interference, no other botheration from local transmissions and all these things. So this is one of them. Apart from this, which is not mentioned here, is there is a effort by UK's Cambridge group, which is the REACH, the experiment which is coming up. So all are basically in the global signal experiment domain. This is the
this SARAS is a very different kind of antenna, but Prism and edges, are they similar kind of antennas, or is Prism very different from?
No, they all are a little bit different. Prism has this kind of a hibiscus pattern, so a petal-like structure. So, and edges, the current one is very flat, and it was also, they just keep on changing it little bit to modify from their high band versus low band. But SARAS is really innovative. They're coming up with different kinds of, they had this kind of fat dipole initially, and now they have this kind of a monopole-like structure, which is basically to reduce the achromaticity of the beam. Sorry, chromaticity of the beam, not the achromaticity.
Yeah. For edges and Prism, what is driving their shape? Like, how do you determine whether that shape is better or metal is better?
Right. So if you, it's not very pronounced in this particular plot, but if you look at this particular structure, this kind of a feature in a global signal or a single radiometer observation at these frequencies can easily be produced by the band shape of the instrument itself. Okay. So supposedly you made an instrument, it has a kind of its own gain. Okay. What we say band pass or a gain across the frequency channels. Now that also changes depending on what the structure is. It can also change depending on the your heating and cooling. It can also change depending on the conditions, ambient conditions, everything. So
is it difficult to take care of that if you calibrate if you know it precisely what your gain pattern is, then you can correct for that.
Yeah, but you have to realize that RF experiments come also with the thing that how good you can know something, because you have to ultimately measure it. Okay. And when you measure it with any other, like the only option, because of the low frequency, right? You cannot even take it to an anechoic chamber and understand all the entire property, because the chamber has to be extremely large, because you have to do it with this far field conditions. So at lower frequency, this Fraunhofer condition, that you have to be out to that level to actually measure the far field radiation pattern. So those becomes very tricky. Okay. So accurate measurement of those instrument property are also difficult, and sometimes they also keep changing. So the major goal is that because you have some kind of this kind of funny spectral shape in the signal, you want your band pass response of the instrument to be extremely flat, quote unquote, because this flatness has to be also quantified. And if the problem is not about just to have a different spectral property in this gain, but also the gains should be stable across the time, because you are also looking at something like hundreds or thousands of hours of observations to actually detect the signal. So your instrument has to be stable across the entire time. So that's the main goal when people are looking at these different funny shapes. It apparently looks funny, but there is some engineering background to it. Does it answer your question?
Yeah, thanks.
Yeah. Okay. So this was the results put out by Aegis in 2018, and actually quite started up the discussion, and a lot of people started discussing about all these things. What they said was they tended to detect this absorption trough, which I think Amul was asking me about in last slide. And they put this redshift range between 20 and 16, something like that. But the most striking, there are two main features which we think is most striking. One is this is extremely broad, and this is extremely deep, which is because around say 0.5 Kelvin almost. Okay, so that was never predicted by the models which existed using normal physics, normal astrophysics and all these things. So then the theorists also went back to the blackboard. There were several models being proposed. One set of models talks about dark matter annihilation at higher redshifts, which may cause all these troughs to deepen so much. Another set of models ask for much higher radio background to cause this kind of depths. We have tested our extraction codes, which will come towards the end of this talk, and we could recreate or fit to the depth of the profile, but we find it difficult to actually recreate the width of this profile. That was our group's confirmation for this, but I think there are lots of papers, and one of them, I think Girish is also a co-author, and he has proposed a lot of reasons why it can happen. A lot of other people have talked about these reflections. So they asked for making this ground stream a little bit bigger. So, and another thing is that if you're looking at this frequency, this redshifts, it comes to around 88 kind of megahertz. So you know what is there in 88 megahertz. 88.5 megahertz to 110 megahertz is FM band, our FM music channels, and that is there everywhere on the earth. Even if you are in a pristine location where you don't have any civilization, you still see, and MWA has seen reflections from the moon for these FM band stations. So that's kind of few worrisome things about this particular tentative detection, but I will leave it there. So that was the global signal experiments, which is you're looking at with a single radiometer, you're looking at averaging over a large part of the sky. Here we are talking about several interferometers where you are trying to understand the spatial fluctuations. Okay, what is actually happening? So you're not actually doing the full tomographic imaging because of lack of signal to noise, and that is also true for LOFAR, MWA, paper, HERA, GMRT. But SKA1 has some predictions that with sensitivity, we may be able to detect a large size Strongman sphere or H2 bubble. Okay, so GMRT initially started from the Welipens group. They have done a lot of experiments with GMRT at 150 megahertz using a novel technique of using a pulsar for phase calibration, and their upper limits came out in this Greg Passiger's paper in 2013. Paper did quite a bit of phased deployment, starting from 64 antenna to 128, and they had a lot of interesting initial results, upper limits, and they finally put one, but that was retracted. But I think that was rescaled by a factor of 5 or 6 later. MWA phase 2 is starting, but I think the phase 1 has a lot of upper limits. I will summarize them in the next slide. And LOFAR also has initial upper limits sent in 2017, but they also have updated upper limits, and all of them have been able to do nice development of several pipelines, several foreground extraction, avoidance pipelines, which is useful. So this is what the current status is. You have all this predicted power spectrums down here. These are the sensitivity from SKA and NUFAR, which is one of the LOFAR offshoot. And here is all the upper limits. So if you see the MWA ones are over here, there is one from LOFAR, very recent, Florian Martin's one here, but nothing close to anything to the actual signal. So the predictions are that SKA is required to go for more observations, and so that's what the planning is. So I will just come to that. So what is SKA? I think this group knows. For starters who do not know what SKA is, it's the Square Kilometre Array. It's a worldwide consortium about a lot of countries, including India, and it will be one of the largest radio telescope built so far, spread across 2 different continents. One will be in the low, which is our interest for this particular talk. It's in Western Australia, and it will be from 70 to 350 megahertz. 50 megahertz was the initial thing. Now it is 70. And there will be several dipoles. So it's not like the GMRT. GMRT is about the dishes, but as you move lower and lower in frequency, the aperture array concept is more prevalent. So you can actually make it cheaper, and you can actually plug in more number of dipoles, which you can phase up to mimic one dish at the end. I will show you some animations next slide. So the idea is there will be grouped dipoles, 256 dipoles in each station, and there will be several such 512 such stations, and spread across maximum baseline will be 65 kilometers. The striking part is that you have you see this data output from the telescopes. Now we do observation with GMRT, the upgraded GMRT, for 6 hours. And with the highest resolution in time and frequency, we kind of accumulate data for about 2 terabytes or so max. Okay, this is, we are talking about 157 terabytes of data acquired per second. Okay, so this is quite a regime change from what we are doing right now. Initially, when we started off our careers, I mean, there was this, we used to make several copies of data. We have one night of observation, you keep several copies so that you don't have to go back to the telescope again. Now, the understanding is that it may be cheaper to re-observe some observations than to store that data to the finest details. So it's either that's the basic game. So that's the mid, the SK low. The mid is in South Africa, that is from 50 megahertz to 14 gigahertz. So relevant for post-EOR studies, but not for the topic of this particular talk. So that's have dishes, and in contrast to the SK1 low. Okay, let me see that. Okay, so this is a slide to compare the relative sensitivities for different telescopes. So this is what the current JVLA or Jansky Very Large Array in New Mexico stands for frequencies above 1 gigahertz. It has a small coverage near the P band or 300 megahertz and also at 74 megahertz, but not comparable to what UGMRT currently has. And this is the LOFAR HBA or the high band array and LOFAR low band array over here. This is a predicted sensitivity from SK1 low and SK1 mid. So you can still see, even if SK comes up, till SK comes up, I think UGMRT is a very sensitive telescope for this particular wavelength bands, and people are really making use of it. And we'll show you some fantastic results which we have obtained using this telescope. Okay, so this is a animation which is, you can also see it from the SK website. This is how the dishes will look like when it comes up in South Africa. Okay, and the next, this is a bit different in concept. So it's the aperture array. So each of these circles actually consists of 256 dipole antennas, and they are phased to mimic one dish. So each of these tiles, which we say is kind of a single dish. And of course, there is a possibility of producing multiple beams on the sky from each of these tiles, but that's a separate talk and separate things to discuss. For our case, this is a single dish, so you do correlation among any two such tiles and get your visibilities for the interferometric output. Okay. I can run it again just for, oops, sorry, I went to the next slide.
So Abhirup, so one of the main challenges in having so many antennas is computational, right? How you correlate all these things. So is this regularity of the dipoles, how this pattern, is it related to making the computationals easier? Is that one of the factors when you design the geometry?
No, the geometry is circular, probably just ease of approaching each of the dipoles. The total the size actually and the total number of dipoles actually accounts for the collecting area. Okay. And the beam also, if you're phasing up the entire tile, you're making a sharper beam than if you're taking a subset of this. That also is there. So you can actually use a subset of such dipoles and form one beam on this part of the sky and another subset of dipoles to form another beam. So that's the trick which happens in the beam format, one of the electronics devices there. And you can form multiple beams on the sky and observe two parts of the sky simultaneously. That is possible. Okay.
No, I was just asking because in this each patch, the grid seems to be very regular.
Yes. So that
is that to take advantage of some FFT?
Yeah. So there are several patterns of laying out the dipoles in the dish, mainly to minimize the side lobes. Okay. Appearing of that. But recently there is a very recent find out from the engineering development area. So there is one such tile now under deployment in Western Australia, and there was a recent result that there is some kind of a, using the pattern which is there. Sorry for that. Yeah, thanks. So, so there was a recent result that using the pattern which was created, we find there is a resonance at 70 megahertz frequency. So that's because of we're using some pseudo-random pattern of laying out the dipoles inside this 256 inside this circle. Okay, and that has created the two antennas to come very close to each other. Okay, and that causes what is called the crosstalk. Okay, so that was now going further to some in engineering investigation, and we are going to they're going to basically make it a different layout. So to answer that, your question partly is that you have this one single area, so you can want to pack as much as dipole you can, provided there is no crosstalk, there is no issues, engineering issues of approaching each of those them there. Okay, so there are several patterns, like there is a Vogel pattern, there is one pseudo-random pattern, and so I think there was some optimization being created, mostly to reduce the side lobe of the tile beam.
Okay, thanks.
So yeah, so I had a question.
Yeah.
So again regarding this this pattern of dipole antennas.
Correct.
Now since the one of the aims of having many dipole antennas is to take care of the phases, right, between them.
Yeah.
And when you do signals and systems kind of thing, you learn that if the pattern is very regular, then you have redundant information. So is this pattern really regular, or maybe I didn't understand from what you're saying that maybe what looks regular is not exactly regular, but there is some irregularity which is important for getting more information.
Right, but see, this is actually, you're not correlating between each dipoles here. What you're doing, you're basically taking the entire thing and phasing them up. Okay, what you're doing is you're correlating between two such tiles. You can of course do the correlation between individual tiles, but that's not the goal, because individual dipole beam is too large. Okay,
that's
it's horizon to horizon. Okay, till you phase it up into this large dipole, 256 dipoles, your beam does not become sharper enough to point to a particular part of the sky.
Okay, I understand.
Okay, so one way you can see is that if you phase up a subset of these dipoles, you can actually steer your beam across the sky. That's the final goal. Okay. But that was tried by MWA to do it, but there was some problem with the accurate information of the beam, because if you look at the main problem of edges was the beam. One of the part is this chromatic beam. We need to have a good handle on the beam, which unfortunately the dishes gives us a better response to the beam accurate information than the aperture antennas. Okay, so the initial idea was that this will be done in a way that if you, at a given time, if you just phase up a subset of the dipoles, you can have the beam on any part of the sky. And if you keep on changing these weights, you can basically steer the electronic beam across the sky to track a source from rise to set, as you do with the parabolic dish. Okay, but there are some issues which the initial pathfinders or the precursor like MWA found in that particular approach, because your accurate beam information is lost, and that is very much required in post-processing to actually remove the foregrounds and get the signal. So they're trying now with hybrid. You point to a part of the sky, let the sky drift about you, point another one, and then drift, and so and so. Okay, I think some similar analysis has been done by both Shiv and his student Akash, and they have published their results, I guess. Okay, so moving on. Okay, run faster. Okay, so all these are fine. The telescopes are really good. There is a lot of engineering progress. the signal, the theoretical work behind defining the signals is very good. But here comes the other problem. The fantastic sky which we have in front of this entire thing is a foreground for our detection of this cosmological signal. And that has to be correctly, accurately subtracted from the data set to be able to extract the signal. So that's the major game in this. And the problem over here, if you look at the global signal point of view, here is the mock H1 21 centimeter signal over here, down here. Sorry, not that, this is not the global, it's the angular power spectrum, sorry for that. And this is the 21 centimeter signal power spectrum, angular power spectrum. And here you see the other contributing factors from the foreground. This is the galactic synchrotron radiation. These are from the extragalactic point sources. These are free and the free emission. Okay. So all these are several orders of magnitudes higher, stronger, brighter than the signal you want to detect. So you have to actually remove all this accurately to be able to extract this particular signal. That's the challenge. And so if you look at extragalactic sky, which we can do with GMRT, you see this is the point source CDF basically of the point source distribution of the extragalactic point sources. These are from several different surveys done so far. One of the best surveys done so far is Cosmos. And there are all sky surveys like FIRST and done by VLA at L-band. And again, the current generation telescopes like the MWA has done a GLEAM survey, which is very useful, but lacks the resolution to essentially resolve out each point sources. This is the characteristics of the point sources, which is going to be important to the information required to be able to remove the point sources and extract the H1 signal, whether in power spectrum or in global signal. But on top of that, those are the actual sky issues. But here is a problem which is created by human. This is a particular time and this is a frequency. And you can see from just a visibility plot, okay, from GMRT, this is from our observation in the band 3 of UGMRT. And you can see several this radio frequency interferences created in the GMRT, even at the higher frequency. If I go to the lower band, which is band 2 at 150 megahertz, you see a lot of more such miscreants which can offset your signal. Now, all such individual RFIs can be blocked, but when you're blocking the RFI, you're also blocking any signal which is coming through that particular channel. So only your hope is if you have a very high frequency and time resolution, and your RFI radio frequency interferences are kind of intermittent and narrow band, you should be able to flag them out or remove it, excise them from your data, and recover the good data in intervening channels. But sometimes that is also not the case. Sometimes that is also a wishful thinking, because RFIs are also broadband, they have harmonics, and so you may have an out-of-band RFI which can offset your signal in band. So all those are very gloomy picture to show in the process of detecting this very faint cosmological signal. So that this kind of things makes the case of going to the moon or far side of the moon and to create a space mission out of this to be able to have a very clean spectrum are the major reasons of proposing such experiments. So that's RFI, and now let us look into some of the development of how do you actually be able to, so suppose you do not remove, but is there a parameter space inside your data where the signal, the cosmological signal actually dominates over the foregrounds? So one such proposal actually came by us, our work earlier from my thesis, that if you actually split this parameter space in the spatial modes, the K modes, basically the power spectrum modes, into K parallel and K perpendicular, where K parallel is corresponding to the line of sight, because your frequency is basically is redshifted frequency. This is the line of sight distance. And if you break it up into that versus the transverse direction, actually there is a sweet spot where and the signal being everywhere, I think there is a window where the signal wins over the foregrounds, because foregrounds are generally not that much spectrally, doesn't have that much of spectral feature. So their Fourier transform along the K parallel is limited only to lower and lower Fourier modes. Okay, so they're expected generally to be a smooth function along frequency. So that was one proposition where you kind of have a sweet spot in this K parallel and K perpendicular, which you can utilize without even going for removal of this very bright foregrounds. So that's a technique which is called foreground avoidance. But remember, this is only a sweet prescription, which is only valid when you have nothing else, an ideal instrument, no spectral leakage, no mode mixing. Otherwise, you will see spikes coming, and I will show you some pictures, and eroding this entire window of opportunity. Okay, so another going forward was we have shown the extragalactic foregrounds. Now there is also galactic synchrotron radiation, which is also a very strong diffuse foreground, which has to be removed. And we have made some observations which put some kind of a handle on what this angular power spectrum is. So we have one of our students, Arnab Chakravarti, have done his thesis with observations. Now with GMRT, you cannot actually go to the 150 megahertz band because it's very, very crowded with more RFI, and there's issues about the primary beam and other things. But now we are having good results. But this earlier work by Arnab, which has actually been related to this one particular field called LIS North 1, which is a very well-studied field. The idea of the project is that you actually look into a very deep field and you try to understand and constrain the foregrounds in this particular area. And the reason to choose a very well-known field is that you have other multi-frequency observations, and so you can constrain and understand and do other other different parallel secondary sciences with the same data. So one of our major finding is that you have this, this is a image made by UGMRT at the 300 to 500 megahertz frequencies. And you can see that if you look at the central part of the field, the sources behave very well because they're either point sources or extended ones. But as you move out, you can see particularly this area marked in with circles, you can see there are a lot of undulations near about the bright sources. And there are typically the features from either calibration error or some interference patterns as remaining in the data, and so on and so forth. But one of the major structure is the ionosphere, where the effect of the ionosphere actually increases as you move away from the field center. And if you see, if you're going and lower in frequency, you see this effect from the ionosphere, ionospheric corruption actually increases. So that requires you to actually undertake something called direction-dependent calibration, which again is something under development for UGMRT purposes, and some of the results can be showing that effects. Okay, so you can see that if you're using the GMRT observation at 300 to 500 megahertz, and you're using a very small part of the band, and we're using the direction-dependent calibration versus a larger part of the band, and you're using only the direction-independent calibration, you can see there's a difference between. So definitely the one which is a better image doesn't have too many bothering effects, bright interferences, that is basically well calibrated. That is the image which is showing you the better calibrated data using the direction dependent calibration. However, we have been only able to use it on narrow band and not on the wide band. And so you can see the difference that what it makes. That means that the net outcome of this slide is that you have to use some calibration technique to take care of these direction dependent terms. Direction dependent terms can occur because of the ionosphere, as we all know, that as any radio wave passes through the ionosphere, because of this plasma electron content, it gets corrupted by the ionosphere. And so you have to use direction dependent calibration techniques to actually take out the effect of the ionosphere from the data. In addition to that, if there are any beam imperfections, any beam not adequate knowledge of the beam, that also actually is taken care of by this direction dependent calibration techniques. Okay, so with that data, what we tried to do, we have tried to just put a kind of a bound on what does the angular spectrum of this diffuse synchrotron radiation does. So we have found, and we have essentially parameterized in terms of the beta, which is the index. So if I just, sorry, rushing through a little bit because I'm running out of, just show you the final plot of this. Yeah, so this is the final data product which we have got from this particular work from Arnav, where we have actually constrained the diffuse synchrotron radiation from this band 3 observation of GMRT, and we have put an upper limit on the index. Okay, we'll skip this. Yeah, sorry, one thing to say, this particular exercise with the band 3 data actually produced finally a very, very deep image with the GMRT at this particular band, which is the deepest image we have produced so far. That's what we have thought. And we just observed for like 26 hours, which is not that huge, big a deal. Okay, we'll skip this. That. Yeah. So now this is a nice result because so we have shown you the angular power spectrum. Now this is angular power spectrum for every frequency beam going from 300 megahertz up to 500 megahertz. And you can see this is the points which we are showing. Suddenly, this is an interesting thing. We see a tentative break in this angular power spectrum near about 400 megahertz, which is quite curious because it generally should not occur at these frequencies and should occur at a lower frequency than 300 megahertz. So that's what we are trying to go after and see if we can get more observations or any other fields which can show the similar thing, or is just the effect of calibration for our data. If you want to talk about more, I can discuss offline. So that was angular power spectrum from our particular work, and this is we have converted that into. Let's just go to the final. Yeah. We have converted that to this two-dimensional power spectrum and actually have put the first limit on this full three-dimensional power spectrum at this frequency, which is the post-EOR. That's the best you can do with GMRT. But we are still off by many orders of magnitude because this is just a 24 hours of observations. And we have a prediction that we probably need a few hundred hours to actually go any close to the detections over here. But these predictions from the theory are actually coming from very basic simulations. I mean, one thing we are trying to encourage the theorists in our group and everywhere is that if we can find a better theoretical model at this post-EOR era to compare with, we may actually start with few hundred hours of observations or more. We can actually start ruling out certain models at the post-EOR region. But all of my theoretical friends are saying that this is very, very boring science, and the post-EOR era not as exciting as the EOR and cosmic dawn. So we have to see how to go about this particular thing. But it can be done with GMRT as well, and it's a nice significant result which can be put out by GMRT at this particular frequency. Okay, we leave it at that. We skip this. So what we learned from the GMRT is a nice input for how to go about with the future SK observations, because unfortunately we do not have any SK pathfinder, SK precursor telescope in our collaborations. So you have to be either go to MWA or you have to go to the LOFAR guys. But those data is not available, but that's not quite correct. The MWA has released their quite a few years of observations currently, and if you are collaborating with some people who are in MWA, you can actually be able to analyze some data. But here in our group and in India, we are trying to make an end-to-end pipeline so that we understand this nitty-gritty of all the observations, what are the nuisance parameters which can go into any particular observation, and design better signal extraction pipelines which can be utilized then later on for SK like telescopes. Okay, one such effort is undertaken by one of my PhD students, by Sheila. She has developed an end-to-end pipeline which takes in any kind of telescope model to begin with, and the foreground models and the signal as predicted by, currently we are using this Rian Yuga developed by Suman Majumdar and his colleagues, as well as Andre Messinger's 21 centimeter fast as the input. But we will be happy to use any such signal models. I know Girish has a few, and we can use that at the beginning, and then we can actually produce synthetic observations through the telescope of our choice. Mostly it is SK, but we can also simulate Hera as well as MWA1, 2, you name it. Okay, and then what will happen is that in between we can also put in the foreground sky in the observations, and then some parameters like any offset in the calibration errors or in the beam model, which we can actually try to study by this end-to-end pipeline, so that we can understand whether our signal extraction techniques are robust against these minor fluctuations in the telescope and foreground parameters. One of the techniques which we used as our from our end as a foreground signal extraction technique is using the help of machine learning. So using artificial neural network to do that. Since time is short, I will skip the basic premises of artificial neural network. If you want, we can discuss that later. But just to give you a handle on what we have done with that. So we have taken the input signal power spectrum from Rian Yuga, which is a package developed by Suman Majumdar, who is also a fellow faculty member here in IIT Indore, and his colleagues. And we have inputted foreground power spectrum from our observational priors from GMRT, but also which are also consistent with any other statistical models developed by other groups across the world. And we have processed that, we have trained our neural network using that. So we have these three parameters from the input signal power spectrum, the N-ion, minimum halo mass, and the ionization fraction. And we have trained that and then predicted the signal and the foreground parameters from this data. So what we are seeing so far is that under even a stringent foreground model without any ionosphere or any other parameters, I think we are still able to recover this signal back with confidence. This signal parameters are working fine. But here a lot of other steps are there which I have not included, lack of time. But there are students who are working currently who are trying to understand the effect of ionosphere, primary beam pattern, and all these things and how that will affect the detection of the signal parameters from the 24 centimeter power spectrum as observed by SKA or other telescopes. Just because we started with edges, I just want to show this particular result, which is now published by Madhurima's work, which is who is also one of my students. So we have actually taken this this particular result, the data which was shared by the edges collaboration, and actually have tried to use this one model, which is actually putting this to the excess radio background. Okay, and we have tried to draw inference: is it real or not? So what we have seen in our study is that we can recreate this depth of the tentative signal detection, but we cannot recreate the width of the signal. That's what's our inference in this paper. Yeah, that is what it came. So we have actually recreated the depth, you can see, but not the width of the signal, which is shared with us by the edges collaborator. But we leave it at that. Just before we, I think I have 1 minute. So just to advertise one project, which is very exciting to us. In the last call for proposal from ISRO, there was mission opportunities. And one of the proposals which we have proposed, I'm a co-I, the main team is, the engineering team is from Pune University. And this is a proposal of flying something at radio telescope at lower than 16 megahertz. Okay, this is a every radio astronomer's dream, to try to see the spectrum below sub megahertz, basically, because we cannot do it from the ground because of the ionospheric plasma cutoff frequency. So this is one of the missions which is selected for the phase, what they say is concept study. And that is been funded, seed funded, and now we are coming close to that particular phase. And there are only 3 others, and one more also from the radio is a team from RRI called Pratyush, but they are looking into the same principle, similar spectra, but at a higher frequency, which is corresponding to the cosmic dawn and EOR, while this particular telescope will be looking into, if funded and if flown, at the cosmic dark ages. So this is one of the very initial telescopes going to be flown, if approved, and to detect signals at cosmic dark ages. Okay. So these are the several things. So initially, the exciting stage is that we have gotten selected for a stage 4 PSLV flight. So that basically means is, when a rocket is launched, the payload goes out and detached, and the lift vehicle actually goes back to the Earth. Okay, but it stays, this 4th stage of the PSLV actually stays on orbit from any time varying to few days to few months. So there was a mission of opportunity for designing experiments to be flown in that 4th stage of PSLV. So what we have been approved is we can actually fly now an engineering prototype of this SIMS payload in that, and that is approved actually. So that will give us some more insight on whether this particular prototype is working or not, and design a better one for the future flight for the phase 2, which will be around the moon and doing various other things, but including that, if we get a longer life cycle, then we can also do a hunt for this cosmological signal during the dark ages from the global signal. Okay. So with that note, I think I just leave it there. Thanks a lot for listening, and questions, if you're still there.
Thanks, Abhirup.
Abhirup, you mentioned GMRT at low redshifts. What is the status of EOR efforts using GMRT?
Yeah, it's a good question. I mean, we have, I was tempted to show, but we have a 150 megahertz image of the same field of LIS North 1. We just are just doing the final analysis for the beam correction, and before that happens, I would not like to share that. But yes, the situation is pretty bad. This is the one. This is 300 megahertz, but we have an image for about just 8 hours of observation in the band 2. The situation is much worse than this particular frequency, and mainly because when initially it was 16 megahertz band only, but when they became wider band, they make it 120 megahertz. And what happened because of that widening of the band is that there's a lot of out of band RFI which is now coming in, and it's completely flooding the entire thing. But it looked very bad when we took this observation and did some initial study. But now we have another PhD student after Arnab, she is taking a better look at it, and we think it is doable, but with a lot of data loss, almost like 50 to 70%. But it is still doable. So we have an image which is not bad, but much higher than the theoretical sensitivity, which is predicted. This is obvious because we have a lot of data loss. We can clarify. And but it still can be done. But I think a lot of effort has to go in to actually restrict this RFI, and still you can do. But if you are looking for EOR, I mean, I won't be that much optimistic right now, because I mean with the ionosphere, it is actually much located near to the magnetic equator than any other telescopes. So if you look at the latitude of MWA or proposed SK1 low is mostly towards what they say is mid latitude. Okay, it's not quite near the equator, but GMRT is the only telescope low frequency which is just near to the magnetic equator. Okay, so I think the ionosphere will always be a problem, but right now we are having a nice extended minima, not so great solar maxima. So I think it's good to carry out our observations now and make the best use of band 2 as much as possible. So that's.
Oh, it's really nice.
We are trying. We got another 24 hours this cycle also, so we will keep trying, keep pushing it and see how far deep we can go.
Great, thanks.
So, Abhirup, can I ask a question?
Yeah, sure.
Yeah, hi, this is Shreyash here. Thank you for the wonderful talk. So, if you go back to your very first slide, I wanted to get your thoughts on, you mentioned that from Epoch of Reionization, you're basically learning about the first stars and the galaxies, for how the galaxies formed and so on. So, I wanted to get your thoughts on how model dependent is our understanding of the physics of these first stars based on what we measure. The measurement is either a global spectrum or a power spectra. So how do we go from the power spectra to the physics of what happened at reionization and the first stars, and how well can we understand it?
Yeah, it's a nice question. I mean, I think so. If I may answer, so the global signal is already under question. That okay, if we actually do the power spectrum, if we expected that global signal will be a quick answer. So that was initially the formulation of that. But now what people are actually debating is, in the day and age of this interferometers, is global signal still a valid way to go? Do we learn anything? But I think there is a lot of synergy between both, and you can actually verify one with the other. If I follow the models clearly, there is a lot of degeneracy between parameters. Like we can see that between the foregrounds and some of the signal parameters, a lot of degeneracy. So when I'm doing my ANN network, if you want to simultaneously estimate both the parameters, you cannot do it, because there is you can clearly see that the synchrotron slope and this EOR global signal, they almost look similar at a different state. So these kind of things are difficult to detect. If you see a absorption trough, fantastic. That's a good signature because it's a sudden spectral, change of shape. So the inflection point is there. So you can go after that. But if you see just a very low lying, falling off very smoothly, it's a problem. Okay. Similar thing happens with the power spectrum also. It's almost shapeless. Okay. Till you have this kind of these bumps and wiggles, which are corresponding to these bubble sizes, what people are predicting, or mini halos or other things. So you need some sharp features, frankly, in the power spectrum or in the global signal to be able to go after it and detect them. Okay, and unless you have that, so I think you need both in some sense. And definitely there is some, but my bet is on, you look at the image, finally. You have tomography of the IGM and you can see a hole in the sky. That will be my 2 cents. But till that comes, we have to keep going like CMB. It's a difficult problem. So I think, do I answer your question?
Yeah, thank you. So I think you answered most of my question. What I was trying to go further was, you mentioned that there are these baryonic bulk flows and you want to understand how galaxies are forming and evolving. And assuming that we do see these bubbles in the interferometric images, how I'm trying to understand how we go from those interferometric images to the parameters of galaxy evolution at that time.
Not galaxy evolution. I can say that there is these parameters, like you can talk about the ionization efficiency, the number of photons produced per unit mass or something like that. All those things. What you basically, you think about the ionization front equation, right? And think about what it started from. So depending on what is your initial quasar properties are, you can relate that to the whole size or something like that.
I see. Okay, so then it becomes simply like a H2 region kind of a problem.
But it is not in equilibrium, but it's still growing.
Sure.
So you have to
okay. Yeah. Okay, makes sense. Thank you.
But I mean, you have in-house experts.
So at that point, it becomes sort of simple, quote unquote, simpler physics. It doesn't involve. Is that a reasonable thing to say?
No, I mean, there are a lot of other things, like if supposedly you have this coupling coefficients and other things which are not properly known in some sense. What is this effect of this X-ray, efficiency and all these things? So there are a lot of other parameters. I just try to put a simple picture.
I see. Okay. Okay. Sure. Thank you. Yeah.